right. Gonna be talking in a minute. G'day folks, welcome to our Friday lecture for COMP2300. Great to be back with everybody. Just gonna say hello to you all on the stream. Make sure my restream is working. I've got some viewers on Twitch. Cool. So we're pretty much ready to go. Just gonna make sure I've got my chats available on this screen. 11 in Twitch, few here on 4 on YouTube, and then unknown number on Microsoft. Okay, that one can go away. Great to have you here. We're really starting to get through everything now, aren't we? End of week 11. So things are probably getting pretty serious for you with in terms of workload from all of your other classes. I just want to send a message out to everybody just to hang in there. We've all got big stresses getting towards the end of the semester. I know you students typically have a lot of assignments in the last couple of weeks. We lecturers also have our assignments, which would be creating exams, making sure everything is getting marked, and getting everything organized to finish up the course. So, you know, we're kind of all in it together. I know it can sometimes feel pretty tough, but we're all feeling it. So we're going to get back to our topic of architectures today, our final topic for the course. Next week is back-to-back all revision to just go over all the ideas in the course. And I think it's a great idea in this course to do a big week of revision because all of the topics in this course kind of fit into each other. And sometimes when we're just going through one by one, you don't quite see those connections, and maybe if we do spend quite a significant amount of time zooming out, looking at everything again, we get the opportunity to make a few more of the connections. And that's what I really want to see in the exam, in your responses, is that you understand broadly all of these concepts and that you can put things together in this course. It's not just a big list of individual topics that you know a lot of facts about. It's a whole field that you have a kind of fundamental level of understanding across the whole field of information about computer organization and program execution. For those who are on Twitch and YouTube, I guess, you know, soon we'll be finishing up this course, but if you want to keep up with my lectures in other courses, you can always follow me on my YouTube channel or on Twitch. I'm trying to get 50 followers on Twitch, which is dumb, but if you get 50 followers, then you get to be like Twitch Plus or something, or you somehow get some extra privileges in Twitch. So that might be cool. If you feel like following me, then that would be nice. If you don't want to, then no big loss. It's obviously not required. We have a little bit of information at the start of this lecture. I guess apart from the usual reminders of make sure you're working on assignment 3, make sure you've got your little wires, make sure you have all of your like labs organized so that you know that you've gotten through all the labs, that if you have things you need to go back and look at or ask for help with from tutors, you're taking the opportunities in this last few weeks to make sure you do it. It'll be not a fun thing to be in the situation where you get to the end of this course after week 11 and you realize, oh, I really should have done all of the labs, and then you don't actually have access to our tutors anymore to do it. So make sure you smash the enter the labs button, smash the call a tutor button, and talk to them, engage with them in your labs this week. the other little bit of information is that we're pretty much done with marking for assignment 2. We will either, I'm not sure if they've pushed out to you quite yet, or if they haven't gone out to you quite yet, through GitLab, you'll be getting your feedback directly after this lecture. We'll hit the button to publish the feedback to everybody. The good news is that the average score for assignment 2 is much higher than assignment 1, which I'm really, really happy about. And it shows that the vast majority of students in this class are on top of the material. You're really understanding how to make sort of working, interesting disco board programs in ARM assembly coding, which is just fantastic to see. I was particularly happy that there were so many much improved design documents this time. And particularly, there are a few people out there who have made just staggering improvements in the quality of their design documents between assignment 1 and assignment 2. So I'm really pleased and happy that those people have put the effort in to make sure that their design documents are up to our standard. So just looking at the stats for assignment 2, the mean overall was 65. Like we sort of have said, part 1 is much easier than part 2, so the mean for part 1 is 41. Mean for part 2 is 23.7. There's quite a big range of students. The standard deviation is quite large in this on the total marks. So there's really lots of marks kind of uniformly across the whole marking range, or the significant marking range above 50. Looking at the quartiles, it's kind of nice to see that there's 25% of people who are doing work which we say is at the high distinction level, which is just wonderful to see people putting in so much effort. And I can also see that 75% of the class is certainly doing work which is in the acceptable range. We know that there's another 25% who are still below that bar, and I think there's potential that some things could have gone wrong. Make sure you look at your feedback. If we've missed something in how you've marked it, do get back to us, but we have gone through quite a rigorous marking procedure, so we certainly don't change marks just because you'd like them to change. It has to be because we've missed some technical reason. For instance, if someone's code doesn't work and we haven't had time to figure out why, they might have lost more marks than they needed to, or they may not have gained as many as they potentially could have. Now let's have a look at the marking distributions, part 1. Most people are in the kind of top end, top 5 marks for that one, which shows that everyone's basically doing a great job creating the program to make the little sequencer. For part 2, there's, similarly to assignment 1, there's this sort of even spread throughout the marking range. This time we saw that there were quite a number of people who were getting marks between 45 and 50, and I can assure you that if you got a mark in that, that means that you have done some really amazing work. It was tough to get a mark between 45 and 50 for part 2 in these assignments in this course. So really well done. Looking at the whole assessment, the total marks for assignment 2, there's the mean somewhere around 65. You can see we've kind of got this normal-ish distribution. There's a bump up here between 90 and 100 out of 100 for this assessment. You know, it makes this distribution look kind of funny, but if you think that we could kind of extend this distribution out, there might be people who have really gotten marks which are above what we would consider to be necessary to get full marks on this assignment, and their grades, if we were offering more marks, maybe they could have gotten them, but the maximum you can get is 100. So all I can offer to these people who are in that very high mark category is a, you know, heartfelt COMP2300 thumbs up for a job well done. There were a lot of really wonderful solutions going around the tutor group, and also some in the lower ranges, which were really excellent solutions, but maybe not quite in that top band. But basically, we were really, really happy to see the solutions you all came up with, and I'm looking forward to seeing what you come up with for assignment 3. Ooh, assignment 3. On the topic of assignment 3, just to make sure we did no more interesting comments there. On the topic of assignment 3, we will have assignment 3 help sessions next week on Wednesday and Thursday. That's the same times we've had assignment 3 sessions in assignment help sessions all throughout this semester. So Wednesday afternoon, Thursday afternoon, get into those with your assignment 3 questions. The difference, I suppose, this time is that assignment 3 is not due until the Tuesday after that. It's not due on the Friday. So I suppose there's a bit of a danger that there will be folks out there who are working on their assignment 3, not quite ready to ask a question, and then don't go to the assignment help session. We won't be doing an assignment help session on Saturday, Sunday, Monday, or Tuesday. We just don't do them on the day the assignment's due. That's just too crazy. And then the day before that is a public holiday and the weekend where we will not be doing assignment help sessions either. So the last chance you'll have to get in and ask your tutor about your assignment will be Thursday next week. So make sure that you've started your assignment by that time. We'll be badgering people to make sure they've forked the GitLab repository and gotten started, made a commit before the end of next week. Brent sends around a lot of emails to everybody reminding them to do so if they haven't. Get in there, make a commit, just try a few things out, make sure you understand what's going on, and think of a question and bring them to the tutors in the assignment help sessions. Make good use of that time. So that's all we got to say on that. Assignment 3 will be due in the after week 12 on the Tuesday, and then we will get to marking it, and you'll have your exam soon after. There's been a little bit of great discussion from people on Piazza about the exam questions, and there's also people telling me that their COMP2300 Math 2305 exam is at the same time. Okay, we'll handle that. And there's someone with a finance exam, we'll handle that too. But if you haven't let me know about an exam time clash on Piazza or email, do make sure you get in there and tell me about it so that I know well in advance. We'll start to work through those next week. Okay, I think it's now time to get to the topic for today. Back to week 11 architecture. Now we did start this topic last week, but I think I might just do a little bit of a recap of what we were talking about. Yep, thanks. Adam was just pointing out on teams that he appreciates the last couple of days. We know that the assignments flood in and that this Friday next week is a very popular day to have an assignment due for a course. In previous years for COMP2300, we've just given everyone an extension, like until the end of the weekend after. This year, we haven't bothered with extensions. That's the date that it's due, after the long weekend, after week 12. So there'll be no special extensions after that, I'm afraid. Or no blanket extensions anyway. If someone has a very good reason and evidence about their about requiring extension, we can get in touch. So we were talking about how architecture is kind of taking these standard features, things like windows, walls, standard things that exist in the world, and putting them together in different ways that are creative or might solve certain design problems. Different buildings have different shapes, but they've always got kind of the same building blocks that all go together in different ways. So what we're really talking about in this course is the architecture of CPUs and the architecture of computers. And this comes down to the point of computer organization. How do you organize the components of a computer to accomplish certain tasks? And we learned on Tuesday a little bit about some very early computers that worked with digital technologies, but perhaps relays rather than valves or solid-state electronics. This sort of connects with our OS lectures, looking at some very early computing devices. And then we had a little look at these two kind of, or the broad model which our computers are modeled after, which is the von Neumann architecture, where you can change the program in the computer, first of all. There are some things that used to be kind of in the same realm as computers where you couldn't change what the program was. So they're more like a calculator, right? Or what we think of as a calculator. You would have one thing that it could do, and if you wanted to change its program on those early computers, you had to rebuild the machine to make it do something else. But programmable computers was this new class. The von Neumann architecture, you've got one memory area that stores both your programs and your data. And the advantage of that is that you can read and write anywhere in that memory, and then you can use this computer to rewrite its own program, write new programs, do lots of very flexible stuff, which is really handy. And then we went back to this basic simple CPU slide. This is where we got to last week. A simple CPU where we've got our memory area, our ALU, which is what's kind of actually doing the work of calculating stuff, doing pluses and multipliers and subs and divs. Then some thing to manage code and fetch the instruction stream, get that ready, some stuff to communicate with memory, saving and loading saving and loading the results of instructions or doing letter and store operations. We have a big bank of registers, which are memory as well, but they're kind of right close into the CPU. And yes, the disco board is von Neumann. Adam has just asked a question. Von Neumann is normal. Harvard is sort of abnormal, although there are some aspects of the Harvard architecture which are sometimes come into von Neumann machines as well. The one example I can think of something which is more like a Harvard architecture are the Atmel. I think it's the Atmel, maybe it's the AVR MCUs. AVR, Harvard. Yeah, they're the same thing. The AVR microcontrollers, which came from a company called Atmel. That's where I forgot it. Yeah, the AVR microcontrollers, which they're the ones that are on the Arduino, and they actually are Harvard machines. So they have like two kinds of load. You can either load from regular memory, data memory, or load from program memory. So you have to have two instructions to get from those different places. Anyway, back to this. We're not talking about von Neumann Harvard stuff anymore. We're talking about our simple CPU architecture. And we've got all of these different kind of units that are within our CPU. And we're going to be using this diagram to illustrate a few points in a minute. So you'll see what I mean. Now, one thing, I guess the two things that we're talking about today which are really important are pipelining and parallel computation. And the first one is this idea of pipelining. So we know when we're operating a disco board that we've got this fetch, decode, execute cycle, right? So first, the code management system will load an instruction out of memory. Then that instruction gets sort of sequenced up, decoded, sequenced up, and fed into the ALU, which will do its job, or the data management system, which will do its job if it's a load instruction or a store. And then there will be the executing part. So we have this idea of an instruction pipeline which actually allows the fetch, decode, execute cycle, which are each like an independent thing, to happen overlapped in time. Because if you look at this, our big diagram of the CPU, this is sort of the part that's doing the execution, this is the part that's doing the decoding, and this is the part that's doing the fetching. So there's nothing in particular stopping. If we went fetch, decode, execute, that would be like doing them in sequence, 1, 2, 3. There's no particular reason why we can't be fetching something while we're decoding something while simultaneously we're executing something. So we could be kind of stepping through this system. There's something weird making a sound in my office. I'm not quite sure what it is, so maybe I'll find out in a minute. That's odd. Okay. Weird sounds. So if we If we just enter the analogy zone for a minute, entering the analogy zone, then having a look at a escalator, right? You could use an escalator like this. One person goes to the top of the escalator, they travel all the way down to the bottom, then they get off, and then the next person gets on. So there can only be one person on an escalator at once. But that's not how we use escalators, right? We use it where like a person goes on once every 2 steps. And maybe if it's very busy, we decide to like, you know, social distancing aside, we decide to get over our social norms and even be like right close to each other. One tread of the escalator. Everyone has one tread and is just trying not to touch anybody else. You know, when you're in an airport and it's very busy, everyone's got their bag as well and they're trying to hold their bag in. So we can use this escalator to transport a lot of people and not just one person. And we can do the same kind of thing in a CPU where we have each instruction kind of traveling through this fetch decode cycle. The fetch decode cycle could be kind of like an escalator. Maybe it's going to go down like this. There'll be the fetch stage, then the decode stage, and then the execute stage. And instruction 1 might be at execute, the one coming behind it might be at decode, and the one coming behind that will be at fetch. So we can we'll line up these instructions all in the escalator so that we're doing 3 things at once. Now, this doesn't make our CPU faster to do one instruction, right? It's still, if number 1 enters here, and for the time it takes for number 1 to get all the way out the end, is going to be unchanged. But what it does mean is that we can multiply by 3 if it's working correctly. Multiply by 3 the number of instructions that we can have within our coming through at any one time. So we get higher throughput, but the same latency. You can probably see now Adam Rowland's going to be done there. Adam asked, do pipelines only work if the tasks are being done in different components? In some sense, that's the definition of the pipeline unless you have other hardware, right? If you've got one ALU, it can only do one thing at one time. So we'll talk about other ways that you could maybe have lots of ALUs or something in a little bit. But at the moment, we've only got these 3 components which can be separated out and do things simultaneously. Isabel says a pipeline is also like an assembly line. Yeah, another really good, good analogy there. You're taking an assembly line where there's different people doing a job and each one is distinct along an assembly line. So these people are kind of sitting here working on a box that's going past them, and each one is doing a different type of job. That one's doing job A, this one's doing job C, and the parcel is sort of moving along the line and everyone's doing their job. So you don't just do one parcel and wait until that's completely finished before starting the next one. You get, and the next parcel is waiting, this one's half done and that one's 2/3 done. So here's a simple pipeline. We've got 3 instructions and we're actually going to just pipeline out the fetch, decode, and execute stages. So it'll be a 3-stage pipeline. So on the first clock cycle, the first instruction is fetched. Second clock cycle, that one's decoded. Meanwhile, instruction 2 is being fetched. Now, on clock cycle 3, we've gotten up to execute for instruction 1. Simultaneously, instruction 2 can decode, and instruction 3 can be fetched. Instruction 4 can now be executed at clock cycle 4, and this one can decode, and that one can execute. Cool, everything should be fine, right? We just multiplied our productivity by 3, no problems. No problems at all. Can anyone see what might be a problem, even at this point, with this pipeline. Gabe has asked, I just said a 3-part pipeline. That's a very simple pipeline, and in fact that's the one that works on the Disco board's processor. There are other kinds of pipelines that might be very long, particularly on like your desktop processors. I'm not going to go into detail about them. I think 3 is probably like on the shorter end, but it is possible to have much longer pipelines. And when you do get much longer pipelines, you'll be able to find much greater efficiencies and also more problems. But my question was, can anyone see any issues? See any issues with this pipeline already? And I guess what I'm going to point you to is this point, where we've got number 1 executing. Meanwhile, this one is fetching. No, they don't block each other, not quite. Think about what kind of instructions these can be. And for instance, suppose that this one was a compare instruction, that one was a conditional branch, then what's this one going to be? What instruction is that going to be? Right? Yeah, so Heather Mills has made a really good point here. If an execute takes more than 1 clock cycle, then we will end up in trouble. That will block the pipeline before something else can happen. Yeah, I think Gabe is onto something. I'm just going to open up Teams for a minute. So this is a good point. That's a really good point. So my thought is, if this is a compare, and that's a branch if equal, then how do we know which instruction to actually get for number 3? Right? We kind of have to wait until this instruction has been fully executed before we know what we can get to do the fetch. So this fetch here can't actually go until there. You see what I mean? The other point is that all of these, we've sort of assumed that all of these instructions only take 1 clock cycle. And that's true for if they're just like an add or a sub, but we know on the Disco board that there are lots of instructions that take more than 1. In particular, a load or store will take multiple clock cycles. So if a load or store takes too long on the execute stage, that would be blocking this one for a number of cycles before we could actually get to the execute. So that execute would have to move up here. So there's 2 issues with our we've identified already. Yeah, not having any more suggestions, but I think we've got a few already. So I think it's clear now that even though this pipeline idea is really good, there could be some problems with pipelines in practice. And it turns out that there are problems. They happen all the time. They're called pipeline hazards. So a pipeline will have to have some solutions built into the way that it works in order to handle these. So I'm just going to move on. We've got a slide here from the ARM Cortex-M programming guide, which shows how these 3-stage pipelines work in Cortex-M processors. Got your fetches, got the decode, got our instructions. So in this instance, actually, if we're on a Cortex-M processor, kind of cleverly, if we happen to have 16-bit instructions, then it can actually get two at once, which is nice, because it can get one and then the next one in the same byte, same grab, because of course your loading units can load 32 bits at a time. So the fetch could happen early and be ready for some time later when it could get decoded and executed. So if you want some details about how these really work on Cortex-M processors, like your disco boards, you can have a look at this Programming Guide to Memory Barrier Instructions, which will also kind of explain what will happen if the pipeline ends up blocked at some point. You have to wait until every instruction that's currently in the pipeline is executed. So if you had a conditional branch, that would hold up the pipeline. So everything would have to be executed before you could decide which instruction then to fetch. Because of course, if we did have this instance of having like something COMP2300 somewhere else, right? It could be that we want to execute these instructions straight after, or we could want to, for instance, call that label 1, or we could be executing these instructions straight after. So our fetching unit doesn't know whether to get these ones or these ones until the compare and BEQ instructions are actually executed. So that means that we'll have to flush the pipeline or wait until everything is out of it. Gabe has asked if the pipeline detects something is taking multiple clock cycles, will it be able to pause the fetching to not get a pile up? I don't know the exact details of how you discuss it, but something like that will happen, right? The pipeline is designed in such a way that if an instruction takes a long time to execute, it will be held up. And if a pipeline is blocked by some kind of conditional branch, everything is just held up, nothing goes wrong. Of course, you know it works because your programs don't break on your disco board. Yeah, so now we can have a chat about pipeline hazards. We've discussed a few, but let's just sort of define this. There's actually three main kinds. So the first kind would be called a data hazard, and that's when you might have the outcome of one instruction required to execute the next. So a data hazard, this wasn't really like the problem with branching, right? This is more like when if you had add 3 to 1, and then in the next instruction you had sub 1 to 3. So in this case, this instruction needs R3 in order to actually execute. So if we were overlapping instructions in some way, we would need to wait until we had the answer of R3 ready in order to overlap that instruction with it. So this kind is not as relevant in this simple pipeline example because that kind of outcome is not going to slow it down, right? If every clock is doing one execute, then necessarily this one will be executed and then this one will be executed. But there are some CPUs where certain operations would take a long time, and in which case you could have a data hazard in the pipeline. Another kind of hazard would be structural. So for instance, part of the CPU hardware might be required by 2 instructions simultaneously. So one option would be maybe you wouldn't be able to load and store at the same time if you were overlapping in a certain way. And that could certainly be the case given that the load and store operations take several cycles, you couldn't be overlapping those loading and storing instructions unless you were definitely using different parts of the CPU hardware. So that's another hazard. And then finally a control hazard. So control flow, meaning all about conditional branching. That means that the location of the next branch is unknown until an instruction is executed. So if we have a conditional branch, we don't know which instructions to fetch next until that conditional branch is executed. That's the third kind of hazard. And what can we do about these hazards? Well, so far we've considered that the only solution to these hazards is actually just to stop our pipeline. So as in this example, we start to add empty spaces in our pipeline before taking the next instruction, taking the next part. And these empty spaces are called bubbles. So a pipeline has a bubble in it if there's a component which could be used somewhere, but it's not being used. Bubbles, 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 as far as the eye can see. So of course the worst case scenario would be that you ended up with fetch, decode, execute, fetch, decode, execute, fetch, decode, execute. And in that case, you would never get any efficiencies by having this pipeline set up. But hopefully you are able to, in many cases, overlap things. And you can achieve a higher efficiency of getting instructions through, higher throughput by implementing pipelines. There's other solutions. Another one would be branch prediction. So this is a bit wacky, right? If we've got, suppose we did have this example before where we had a compare and then a BEQ, dot, 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 something, a BEQ label 2, then this was label 1, and that was label 2. So if we see this coming up in our code, there's a few things we could do. We could just not bother fetching things. We don't have to do any work. Just wait until we know the answer and then go ahead and fetch what we need. Or we could make a guess, and the guess could be, for instance, we could just always say, assume the conditional branch is never taken. Just assume that it always fails. So that on that guess, we would always load these ones. Or that one would be always fails. Another guess could be that it always is successful, right? In which case we would load these ones, right? Guess always successful. And if we'd made that guess and then it turned out that the conditional branch failed, well, we would have done work we didn't have to do, but maybe that fetcher and the decoder units weren't doing anything anyway, so it doesn't matter. We haven't exactly lost time. And maybe it is a better idea just to predict some branches. A perhaps more fancy system, branch prediction can get pretty wacky, but a more advanced idea would be that if you had potentially your CPU is smart enough to know what code is being executed, and maybe it will remember something about locations in code that it's been to before. And it could be keeping a tally as it's going through a looped bit of code, for instance. You know, you're doing loops all the time in your code now. Think how many times your CPU would go through that loop. It could be keeping a tally that, 5 times it's been that way, whereas it's only been this way twice. And this means that if it has to guess, we should always load this one and never load that one. And that might be a better guess than just always going the fail route. And then there's much deeper ways of doing this, which I won't claim to understand, but CPU architectures are just getting very, very clever in order to make these kind of efficiencies. There are actually some downsides with some of these policies for finding ways to get around our hazards. And one of the policies is that this one actually, it's been known in the past, branch prediction has been known to kind of leave some information behind that wasn't meant to be there. And it's led us to this issue, led us to a famous bug called Spectre, a security vulnerability, which came out a few years ago in 2018. And basically, this was affected all pre-2019 microprocessors that use branch prediction. So any processor before last year was affected by this bug, and the operating systems had to be updated in order to not potentially reveal more information. I'm not going to claim to have a very good understanding of how Spectre works, but I think that the way it is that when your fetcher would grab some memory that it didn't necessarily need to use predictively, it would leave a sort of a tracing of where it had been, for some footprints of where it had been in the memory cache, in the CPU. So memory is not accessed directly in a CPU. Normally a caching bit of memory which is closer to the CPU is used to prefetch the memory so that it can get it out faster. And you'd end up with some information in cache which you didn't know you needed. And it might have been that was private information that would enable a clever cybersecurity attacker to figure out some secrets about an encryption algorithm. So that's the Spectre vulnerability, which was bad. So predictive branch prediction is a little bit dangerous, or a lot dangerous really. It had to be fixed. And as a result, all of these CPUs which had this feature, that feature couldn't be used anymore. So the operating system basically turns it off. They lost performance, which was not good. This other idea is another crazy one called out-of-order execution. So this is an old slide from Dr. Swift. You're out of order. This whole damn CPU is out of order. We're going to do some out-of-order execution. So this is potentially even wilder. So we're not just prefetching from memory different instructions. It can actually be that your pipeline works better if your instructions happens to be in a different order. So you're an assembly programmer, you're writing out your instructions, and you know that there are some times when if your instructions are in a certain order, they will break your application, and sometimes you have to have them in a particular order, and sometimes it doesn't matter so much, right? If you're just adding some numbers and they're kind of independent instructions, who cares what order they're in? Well, maybe the CPU cares, because the CPU could, if it happened to be in the particular order, the CPU could make the pipeline work, and if they're in the wrong order, the pipeline is not going to work. So this is where it's handy if your CPU is able to fetch multiple instructions, right? Because then it can fetch them and may be able to use some rules to put them in the order that works best for the pipeline before actually trying to execute them. So the pipeline itself becomes a little bit of a scheduler to make sure that your instructions are in the right order. There are some CPUs, not our ARM CPUs, but CISC CPUs, which can actually have CPU instructions that are broken into sub-instructions. That's called microcode, sorry. And that can allow some even more finer-grained sequences to be discovered. Yes, this does sound like it's very similar to other kinds of optimization for other systems. So here's an example. You can have a look at this example in more detail on this YouTube channel called Computer File. There's a great explanation of it. But here's just doing this very simple bit of mathematics, A plus B times C. You would write that in one line in Python or C or Java or whatever. But if you're doing this in assembly, as you know, it's going to take a few more lines. We might do a load to get A, for instance. Then we do a load to get B, then a load to get C. They're all stored in memory or on the stack or something. And then we're going to do an add, adding R1 and R2, and then we're going to do a multiply R1 and R3. Now, if we had the possibility, we might have the possibility of overlapping these two instructions, but it could be that we're blocked because that R1 appears here. So that could be blocking our pipeline, which, as we know, is bad. So if we had a CPU which could support out-of-order execution, it might be able to do something to slow down our approach to this mull and give us a bit of extra time. And what it could do is just switch around these two here, 1 and 2, that one there. So it can do the add first, because this add only relies on these two. Then that add might have time to be fully completed while the loader is going ahead and grabbing R3 out of memory, and then we can finally do our mull. So in that different order, even though from the programmer's perspective it's no different, and actually it makes less sense as a programmer, now it's just jumbled up a bit more, but it could actually allow our CPU to run faster because these pipelines can be intersected more effectively. So that's pretty cool. I encourage you to go watch this video. It's a better explanation. It's got cool computer graphics, so have a look at it. A lot of these things, these little deep optimizations within CPUs, they're not quite magic, but they're kind of the closest thing we've got right now, right? They're very deep secrets, and they're the kind of thing which we don't really know about until something like Spectre happens and it turns out it doesn't work as well as we'd hoped, and we lose some percent that we actually realize that it's there, holding us back sometimes. But how cool is that, right? CPUs that can actually read your instructions as they're coming in and switch them around to make sure that they're in the right order. That's a very impressive assembly line indeed. Now our second topic for today is multiprocessing or parallel processing, parallel systems. So this is where we start to really use our diagram again. Now we're going to talk about a few different types of I suppose, multiprocessing, or ways to do multiple things on one CPU at the same time. How can we do that? Or how can we get multiple CPUs to work together? We had a look at this, a little preview in the OS chapter, right? Or the OS topic, because I think it was on Tuesday we were talking about how a scheduler might take threads and sort of send them out to different CPUs so that they could be run simultaneously, or maybe it was going to switch them in and out of one CPU so that it can context switch between different threads so everybody can be kept evenly. But how can we make the hardware better, or make interesting CPU hardware which can do more things at the same time? So here's the first idea. We've got a few little acronyms now, and the first one is SIMD. That's how you say it usually, SIMD. Single instruction, multiple data. And that's sometimes also called something like vector processing, or processing multiple data at once. And the idea is that you might have a special kind of ALU where you can actually, or maybe just multiple ALUs all lined up, that all get the same instruction code from your sequence of instructions in your program, but they're all connected to different registers. So if you had to add a bunch of numbers together from 4 different registers, you could somehow make one special instruction which tells all of your ALUs to do an add and sends them all registers 1, 2, 3, 4, so that they can all do it together. So this is what this kind of might look like in our sort of wild CPU diagram, right? Multiple ALUs duplicated up, but they're all getting the same instruction. It's just that they've got different registers connected up to them. So when we do this, we will need to have usually some special kind of registers. It often, if you've got a big register, something like a 128-bit register or two 64-bit registers that can be kind of joined together, then that could be used to contain 4 32-bit numbers to do these things. There's a few different technologies that implement this in current CPUs. In your Intel laptop, probably, or certainly if you have a laptop with an Intel chip, it will have support a technology called SSE, which is Intel's older SIMD processing set of instructions, and probably something called AVX, another one. I think it's AVX. It's written down here somewhere. Oh, it's a bit hard to see in this slide, but I think it's down the bottom. On your phone, probably on the ARM processor on your phone, it will support a SIMD vector system called Neon, which is ARM's one. And it's really useful for situations, particularly when you're working with an image or a video or something and you've got to do the same instruction a lot of times on a lot of data. Then you can sort of stream it through these banked ALUs or banked CPU units simultaneously with the same instruction. And you do have to have like these special instructions in the ISA, and then the programming language you're dealing with has to know about them. And usually it becomes a bit of a special case to use the vector optimizations. Okay, so that's SIMD. We can certainly come, I think people often, I talk about these things and then afterwards they're like, wait a minute, I don't understand. So we might come back to them in a second when you've got questions, but here's another idea, another way we can duplicate things in our processor. So before with SIMD, we were duplicating our ALU, right? And now instead we're going to duplicate this stuff, the decoder, sequencer, flags, and registers. Well, why would we do that? And it turns out that this is an idea for doing a kind of advanced context switch. So in the Intel world, this is called hyperthreading, where you can kind of make a virtual CPU core by replicating all this stuff, the registers, decoder, flags, and interrupt. So you could have one decoder and sequencer working on one program, the other working on another program. And each of those programs have their own registers, they've got their own flags, but when they actually go to execute an instruction, they have to do it, take turns using the ALU. Now, why would this be good? Because both instructions can only use the ALU one at a time, right? So how does this actually make our system faster? Well, it turns out that when you do this, the CPU kind of advertises to the OS that it's got two CPUs, really, not just one. And the OS sends one thread to this register, this decoder, I suppose, and the other thread to the one behind it. And now from the OS's point of view, both of those threads are just running completely independently. So the operating system doesn't have to do context switching between those two threads. So even though each one of those threads can only run on the ALU one at a time, the operating system doesn't have to deal with that. And this actually saves a huge amount of time, because every time the operating system has to context switch between one process and another process, it's got to tell one process it's going to go to sleep, or maybe not, just put it to sleep by an interrupt, load up the other process, load all this stuff out of memory. All of these things take cycles and cycles and cycles. And that's basically wasted time. We can't use that time to do any useful work. Whereas with hyperthreading, you can get these two threads that are both using they can't use the ALU at once, but they don't have to be context switched. So switching them between them could be much, much faster. So it can save a huge amount of time from the other scenario of having the OS doing the context switching to memory for us. So that's hyperthreading. duplicating all of this logic here. So here's maybe your chance to think of a question or have a bit of a chat. We're going to have a think now about different kinds of workloads. Benefits from SIMD versus hyperthreading. Yep, and Callum is absolutely right there, saying a context switch in the operating system is probably going to take 1,000 plus cycles. So if your hyperthread can switch in less than 1,000 cycles, which it's very likely to be able to do, it might only take a couple of cycles to get things ready for the other thread to go, then it can be much, much better. Just going to drink my water for a minute while someone thinks of a question. Or are you all too zonked Friday afternoon? Get a nice pad or something. Angels. No, I don't want that. Isabel's saying hyperthreading would help if your different programs are not actually doing a lot. They're waiting for things to happen, etc. Yeah, that's a good point. So of course we've got cycles that are wasted in the ALU if we're waiting for resources or waiting for memory to be ready or waiting for things to be brought into cache. But our hyperthreading would mean that we would be able to use that time by switching out to the other thread which is running. And the CPU will do that for us. The OS doesn't have to do it. Anyone got a workload which would be good for vector processing? Is anyone taking 2420? Any 2420 students in the house? Come on, you can out yourself if you're a 2420 student. Yeah, machine learning. Very, very good point, Aggie. So machine learning will be really, really helped by having these vector processing units, because of course, if you've had a look at some machine learning work, all of your training and inference for machine learning is usually doing a lot of matrix multiplications. And that means you're going to be doing a large number of adds on a long list of numbers to another long list of numbers, and then some multiplies by one long list of numbers with another long list of numbers. And all of those can be really, really sped up with vector operations. So, if you're a 2420 student or a machine learning or AI student, you might have done a lot of computing in Python using the NumPy library, right? And the NumPy library, part of the whole point of the NumPy library is to make sure that your code to do with vectors, to do with arrays of numbers being multiplied with other arrays and added, are all executed in optimized C, which uses all of these special SIMD instructions that are available for your particular processor. So when you do this stuff in NumPy, with NumPy arrays, even though it's a little bit kind of less convenient than using regular old Python lists and stuff, you get much faster results because all of these optimizations in your CPU can be applied really well. Yeah, so we had a couple of great ideas. Adam had a good point about repetitive workloads working better with SIMD. Oh, maybe you'd have to untangle it to do it work with SIMD. I would have thought that that might work better with hyperthreading. Maybe I'm wrong. Okay, we'll go on in a minute. Just sip my water again. Nice to see people jumping in for a few questions and thoughts. So what about we just duplicate everything? And that happens all the time as well. So we end up with multi-core CPUs, or a machine that basically has one memory and a whole lot of CPUs that are connected to that memory to run multiple tasks. And that's going to be a kind of full replication of the full CPU. We don't have to now worry about just running one bit and keeping one other bit static. If we've got two threads, they can just be running in line with each other, each instruction being run simultaneously. Now, I suppose one question might be, are we more likely to use multi-core, or are we more likely to use SIMD, or are we more likely to use hyperthreading? We use all of them. Or engineers don't limit themselves to just one particular great optimization idea. They use all of them at once. I think the only one which you probably don't have access to right now, you might not have, is hyperthreading, because there are CPUs where rather than doing hyperthreading, they just have multiple cores, because why not just add more ALUs? As it turns out, the registers the registers are kind of the expensive bit of a CPU. It takes up a lot of space to have that memory. The ALUs are not as expensive, so in terms of number of transistors. So you may as well just add more cores. So, you know, of course, it often used to be with Intel CPUs that, like, the i5s didn't have multi-threading and the i7s did. And I think there are now i7s which, there's some i7 core, like, I forgot its name, 9900K or something, which has 8 cores but no hyperthreading. So 8 cores, 8 threads. And you can often see if the number of cores is equal to the number of simultaneous threads that can be executed, there's no hyperthreading. But it does have all of those SIMD units, and it does have multiple cores, so that helps as well. So when you do this multi-core stuff, of course, where all of these cores are accessing the same memory, so we need to have our synchronized atomic operations, as we were talking about in the synchronization and concurrency lecture, and we're going to have some programming languages that support some kind of concurrency, either implicitly or explicitly. So implicitly, that means you'd just be coding away and it would be concurrent whether you want it to be or not. And explicitly, you might have some special things you have to write out to make sure that it's doing concurrent operations. So now let's just have a think in the overall. What are all these technologies like? Or can we put all these technologies into a grid? Well, you can. And in fact, people have put these technologies in a grid for a long time. There's this thing called Flynn's taxonomy of kind of processor functions that's from the 60s. And this guy, Flynn, was the one who came up with this idea of measuring things by, like, whether it was single data, single instruction, multiple instruction. So if we've got single instruction, single data, one instruction at a time and one data source, you know, you might have your CPU and it could have one sort of stream from memory or registers. Registers. So we've got one instructions, and one data source. So that's called uniprocessing. That's like normal, right? Your normal one CPU, one instruction, one data source at a time. And your disco board is an example of that. I don't think the disco board has any vector operations. Correct me if I'm wrong, but I don't think it does. And also, like, it was all desktop CPUs until like 2003, 2004. The old Pentium 4 was just one processor, did one thing at one time, or mainly except for those vector processors. Then if we've got one instruction, which can do the same thing to multiple registers, we're connecting multiple data sources, single instruction, multiple data, that's where we get SIMD, SSE and Neon are the examples of that. And then if we go to multiple instructions and multiple data, we're getting, sorry, that was the instructions, I should have done arrows from the top. Multiple instructions going to multiple data, so we've got multiple processors that support that. Now here's where you sort of run out of steam on this, on this taxonomy. It's kind of a weird taxonomy because we could now get to this one. Multiple instruction, single data. Does that make sense? I don't know if that even makes sense at all, because then you would just have, you'd end up with one register. Like you're saying that you should be doing add R1, R2 at the same time mul R1, R2, and then also div R1, R2. But why would we do that, right? It doesn't quite make sense as a strategy. So most of these, whenever any book on computer organization, and every book on computer organization will have in it Flynn's taxonomy somewhere, whenever they get to this one, they'll say something like, oh, this isn't really practical, or no, there's no good examples of this, or like a question mark next to it. And then on Wikipedia, someone has really obviously scraped the bottom of the barrel to find something which could, if you really squint at it, could be a example of MISD processing. But it's not really a popular one because it doesn't really make sense. Oh, anyone talking to me on Restream? No. Oh, we do. So I'm just going to do a few like examples of real CPUs that are like amazing parallel computers of today. It's a bit of a funny thing has happened over the last, I suppose, 15 years in computing. Like I said, 15 years ago, your desktop PC had one processor in it. There were no like multi-core processors, and now everything is parallel. So the world has changed in terms of how important multiprocessing is to regular computing loads. And things are changing rapidly. So when I was a computing student in first year and second year, that was it, like P4, one core, one computer, that was all you got. And parallel computing would be like a special thing for supercomputers or big scientific workstations, but now it's totally normal. So the first amazing and interesting parallel computer of today, which I'll talk to you about, is your phone. So you've all got a phone in your pocket or on your desk or charging somewhere, and your phone is just a normal, modern, fantastic CPU, and it does have multiple cores working together. And one of the really interesting things that they have done with CPUs, particularly those directed towards mobiles, phones and tablets and convertible laptops and stuff, is this idea of not having the same kind of cores, but having different cores. So if we're in this situation where we've just made a multi-core CPU and we've just multiplied our cores, each one is usually equal, and that's probably what it's like on your laptop, which has an i7 or i5, maybe with 4 cores on it. They'll all be the same, but on your phone they don't have to be the same. So in ARM, their name for this technology was Big Little, which was one of their kind of marketing name for it a couple of years ago. They've got another one now called DynamicQ, or Dynamic, which is kind of the successor to that. But the idea is that you have multiple cores on your computer, but they're different. And the ARM version of this, the idea is that we're going to have our little cores, and we'll have several of them, And these ones are going to be, they're called little, which means that they're kind of efficient and power saving. And they're probably running at a lower clock speed. And that means that most of the time when you're using your phone, all of your applications are running on these cores. Not doing anything too spectacular, but they're not running down the battery very fast. And then if you suddenly decide you need to encode a video, it's going to take this thread, which is going to encode the video, and move it over to the big core. And that will mean that it will, for some burst where it needs to encode a video to put it onto Instagram, it can do that only as long as it needs to, and then quickly go back to the little core before it's wasted too much power. And the cleverness with this is making sure that these CPUs, even though they're, first of all, different architectures, they're actually slightly different capabilities. They're not different architectures really, but they're different versions of the ARM Cortex standard. Even though they're different versions, and even though they're running at a different clock speed, can still access the same memory. They probably each have their own cache. I think they have a cache here. Cache, and this one has a cache as well. Cache. And then there's some interconnect which then connects to the memory. So that's really, really clever, right? And it kind of, when you read your computing textbooks, it's frustrating to me because a lot of these computing textbooks that are up to like the 5th or 6th edition, they were first written in the 90s. And they maybe have, or the early 2000s, and they have a view of parallel computing that was built around then. And one aspect of that view is that the main reason to do parallel computing is to make your computer faster. But in this case, we're on purpose making our computer slower using parallel computing, because the most important thing on a phone is not how fast its CPU is, it's that you don't run out of battery. Because if you run out of battery, you can't use it anymore. And that just wasn't the case 15 years ago. People didn't have, there was no computer as powerful as your phone, which was running only on battery, and people didn't assume they had to plug it in all the time. Everyone was just plugging in their laptops and dragging around the power cables. So this is totally used now. I think my phone, which is a bit of an older iPhone now, has the Apple A11, which has 2 big cores and 4 little ones. All of the Apple phones have them now. And likely your other Android phones from different manufacturers will have different variations on this idea to get every power efficiency that they can. Okay, another really amazing parallel computer is your gaming PC. And this is where like parallelism is just taken to the absolute maximum. So there's two people who make gaming PC GPUs, the graphical processing units. One's NVIDIA and one's AMD. I think Intel makes some too, but no one really gives them much credence. Oh, someone's just, Big Lamau is talking to me on yes, Big Lamau is talking to me on Twitch. I'll just reply to them for a moment. You can have 2 threads running on a hyper-threaded core, but they can't use the ALU at the same time. Yeah, that was just a question about hyperthreading. I knew we would have questions. You let me get through all of these slides, and then it turns out there's a lot of questions about it. So the point of a GPU is that it's a highly parallel processor for doing very specific tasks. It's basically taking this SIMD, simultaneous same instruction, multiple data idea to like absolute maximum, because the goal being a graphical processing unit will be to like render every pixel in a scene, where you might have to do an identical instruction on every single pixel as you're doing your rendering process and push all of those pixels together at once. So these GPUs are focused really on bandwidth, or like the amount of data which they can push through these processors, rather than latency. So they're not trying to be as fast as possible, or they don't need to be as fast as possible, but rather push all the pixels through. But they end up just with processing units, which can also be used for general computing if they if the tools exist to actually compile code to run on them. And in the last few years, it's been more and more popular to run regular code or particular loads on GPUs. Again, we're getting back to the machine learning AI stuff. We're doing huge amounts of simultaneous instruction, multiple data operations is useful for training machine learning models. So what ended up happening was that in the past, I guess if you wanted to do some kind of general computing on a GPU, you'd have to somehow awkwardly trick the GPU into running your regular code. Now we don't do that. NVIDIA have this system called CUDA, which is a instruction architecture which allows people to run regular code on a GPU as well as graphics code. And all of their architecture have this name: CUDA units, CUDA cores, CUDA, etc. There's another system called OpenCL, Open Compute Language, which the AMD systems use, and some other GPUs use that, which turns out to not be as useful for various reasons than CUDA for machine learning. But just to give an example of one GPU architecture using CUDA, this is the streaming multiprocessor design for a CUDA Volta architecture card. And there's this is the big core, one big multiprocessor, which has lots of these independent compute units or CUDA cores that can do either one floating point 64 operation, or two int operations, or two floating point 32 operations, and somehow track 32 threads at the same time, so they can also intersect a lot of threads together, because all of their operations might be a bit slow, and while they're waiting for some information to come out of memory, which will be a slower process, they can get something else in the pipeline there and somehow schedule out multiple threads together, which is really clever. Then they've got these tensor cores, which are only really useful for matrix operations. Matrix, matrix, matrix. So this one streaming multiprocessor, CUDA SM, has a lot of cores. It actually has 64 of these individual guys, 64 int, 64 FP32, and 32 of these FP64 ones, and 8 tensor cores. So that's a lot of cores, right? Your regular PC only has 8 or 4 or 8 cores, maybe 2, 4, or 8. This one has 64, but it doesn't stop there, because this is only one streaming multiprocessor. And on the actual card, there are loads of them. The whole card is stacked full of these streaming multiprocessors. So there's one. This is a picture of the Tesla V100 card, which has 84 of these streaming multiprocessors on it. And the more this is a crazy expensive server card. The kind of top-end consumer card, RTX 2080, has 68 of them. So there's still thousands of cores that can all work together. Another question, Big Lamau was saying on Twitch, do we have a scheduler on the ALU to decide and do context switching? I maybe can explain in this instance, your hardware can have some kind of scheduler built in. If you were in the case of doing hyperthreading, yes, there is some kind of hardware scheduler to move between multiple different threads, give them each access to the ALU. Absolutely, there is a hardware scheduler there. And that's how that system works. And in the GPU example, the hardware scheduler is working as well to make sure things are, threads are correctly pipelined to work on all of these thousands of cores simultaneously. Yeah, and when we get to a big GPU architecture like this, these streaming multiprocessors can run different instructions. So they're only like, they're banked on the same instruction within each quarter of this. This much can run one instruction at the same time, this much can run one. And so there's lots of instructions can be done simultaneously if needed to across this whole chip. So what about anything else in the world? Are there any other wild processes we could be talking about? Could we be doing digital computing in plastic? This is something called a DigiComp1, which is a toy from the 60s, a 3-bit CPU. Or maybe we could be doing something else. So this is an example of a quite different kind of CPU architecture, which is useful for embedded applications. And it's a CPU called the Parallax Propeller, which is a really, really cute looking kind of idea for a CPU. So the idea is that you'll have 8 cores, and each core will just, they're very small. This is just an MCU, similar to your disco board. A 32-bit processor, very similar kind of level of complexity. And each core will have 2 kilobytes of memory local to it. And then there'll be some shared memory. And the cool thing that happens here is that your code can run on each cog independently. So you can have lots of tasks running in parallel, which is great for an MCU where you might have to be checking a lot of sensors or something. So in this case, you don't actually have to do interrupts. You can just do polling to get all of your information on the Parallax propeller. And then it has this idea of a hub which moves around the cogs like a propeller, right? And that gives us this idea that it's moving around and around. So it's a really cute idea. Totally normal processor. I actually have one on my desk right now. I'll show you my desk if that's going to work. Just going to check that you can actually see it. Oh yeah, you can. There's the propeller. Oops. On this board, this is a replica computer I was going to show you in a minute. I might not get time to do it today. I might end up doing it on Tuesday. But what about my other alternatives? We get some keyboard admirers every time I show my desk cam in this system. So you can have a look at this video if you want to learn more about how to program with the propeller, programming without interrupts. Pretty wild, but an interesting way to do things. Another system is the RISC-V, free and open source RISC instruction set. So there are some other kinds of processors which use this ISA. I think I talked about this last year, and one of the students jumped in and said, "Oh, we should change from the disco board to this other crazy development board that uses RISC-V." Well, maybe not. I think the ARM ISA is good enough, but this is an alternative with a similar ISA, which is actually open source. So that's cool. And then finally, I guess I could talk about x86. I'm not going to, even though that's the elephant in the room at this point in the course. We've learned so much about ARM, RISC ISAs, and haven't really talked at all about the main kind of ISA that you use on your regular laptop, your regular desktop computer. There's a few reasons for that. One of them is that they're really big and complicated, much like an actual elephant. because they're like this x86 system, they're weighed down. The x86 spec or ISA is weighed down from like historical points of the way things used to be. And it's always been adding to the instruction set rather than taking away. So that is makes it a bit weirder to learn and a bit harder. And then you wouldn't be able to play with your cool disco board if you were only understood x86 assembly. So we don't talk that much about x86. One more thing for the day, and I'll talk about my cool board next time. But you can do you can actually look at a simulation of a whole CPU right in your browser if you want to. I wonder if it's going to work. It doesn't. Oh no, oh there it is. Okay, we got it. Visual, yeah, we got the ARM one. Is this the ARM one? Or is it a 6502? I don't think it's an ARM 1 now. I don't know. ARM 1 gate level simulation. They just changed the URL. Okay, Visual Sim. So we've got a couple of different CPUs which we can simulate here. A whole CPU running in your browser. So this is the ancestor of your disco board is the very first Acorn RISC machine #1, designed in the UK in the mid-80s. And well, there's a great question from Aggie in the chat, which I'll just address in a minute. Here it is running some code, and you can see that it's kind of working at a gate level. Here's each one of these is a little logic gate doing something. And I think the interesting thing to note about this computer is that these are the pads on the outside, which will be connected to other stuff, right, on the little legs of the processor. Like all this stuff here, I think is the registers. So memory takes up most of the space on a CPU, and these ones didn't even have a lot of registers, mainly not registers, but even then it takes up most of the space. Yes, this is a bit computerception. I'll leave that running, and I'm going to look in Teams and see what questions we have. So Aggie has asked, how do virtual machines work, like virtual private servers, VPSs, that we use for all of our web technology? So you know how we had a supervisor, right, in a CPU, and a supervisor call. And the supervisor was allowed to switch between contexts to where a context is a program. So potentially what we could do is run a OS as a context and have something else switching between that. And then we need to have another level of supervisor, which is called a hypervisor. So a hypervisor is a kind of OS which can switch between OSs, running at an even higher level. So the situation gets rather a little bit more complicated in terms of making sure everything is even more secure than it was before. But it totally works. And you can have these powerful computers that are switching OSs between a number of virtual CPUs. And they may not get guaranteed access to a CPU. And you can even like put a whole OS to sleep and then bring it back again without it knowing about it. So this happens all the time now in like the cloud compute world, that we'll have some massive server architecture where there's lots of CPUs all working together, and a hypervisor is kind of sending out whole OSs as a thread for customers who are doing various things with those operating systems. which we don't talk about in this course. So I suppose there's some other course you could look at that will help you understand exactly how that stuff works, but it's not this one, I suppose. As Callum says, there's a good chance the simulation is running inside a VM inside the browser. No, it's running inside my browser, which is probably not on a VM, but this video is coming to you through a VM, I'm sure. Now, I will do a few more seconds of discussion on Tuesday about architectures. I might give you a little, perhaps a fun demo, but I guess what I want to demo is this little homemade PC, which is a homemade computer, which is a replica of the original Apple computer, the Apple I. It runs an famous old chip called the 6502, which is down here. Now I was just going to show you that just for historical interest, but I think I'll do it on Tuesday. And for instance, this one's particularly fun because you can go and make your own if you want. Build your own computer, why not? I've also put up some reading about architectures. All of these, the best place to read about this stuff is a regular computer organization textbook. This one, Essentials of Computer Organization and Architecture, is available on learning.o'reilly.com. You can get access to it through the ANU library. If you just do the virtual proxy and click through, it'll take you to it. Any questions finally? I'm running out of voice quickly, so might have to have a questions in the chat. I guess I'll leave you with this. I hope you kind of get it. We've gone through a lot of things this week, and I wouldn't be surprised if we come back next week into our revision lectures and a few people are like, wait a minute, what was that SIMD thing again? But we will revise it. That's why we have revision lectures. Nope, if there's no more questions, then I might wave goodbye. Everybody have a great weekend, a great long weekend. Enjoy Reconciliation Day. Hopefully we can do a reconciliation activity or have a reconciliation thought about our past and interactions with First Nations people of Australia and throughout the world. And with that, I'll see you on Tuesday. There was a last minute question. Adam said, what course should I do to learn about OSs? Well, you should probably do the operating systems course. What about parallelism or the parallel systems course? And you, operating systems. I think Eric McCreath teaches operating systems, and there's COMP, no, not that one, 2300 maybe is parallel. Eric memes. You'll definitely learn more about systems, networks, and concurrency next semester if you're going to follow through with the 2310 stream, which you may be required in your degree. But COMP2310 is a great course to be doing. I'll put that up on the screen as well. Whoops. Anyway, 2310 is fantastic. You all should look forward to it. I'm probably still the second examiner for 2310. I just get to follow along from the sidelines as Uwe takes you on a magical tour through different kinds of concurrent systems. Okay, with that, I'll wish you good evening, everybody. Have a great weekend.